So hello, this is Muhammad Ashraf from Group 3. So in our project, we analyze how LTI system behave by convolving its impulse. So this is our impulse, and so this is our impulse, and this is our input signals. So the system impulse response is defined as a series of step functions, and the input signal is a shifted step function by started at t equal 1. By performing the convolution, we can determine the output of the system and understand its response to a step input. This analysis is essential in applications like signal processing and control systems.
Next up is methodology. In methodology, we start with our input signal xt, which is defined as a negative step function with a time delay of 1. Then we have our convolution integral. We need to understand it first. It involves flipping ht for h negative tau, then shifting h negative tau by t, then multiplying it with x tau, and integrating for all values of tau. Then let's discuss our range. In case 1, we have t 1 less than 1. In case 2, we have when t is equal to or greater than 1, but less than 2.5. In case 3, when t is equal to or greater than 2.5, but less than 3. In case 4, when t is equal to or greater than 3, but less than 3.5. And finally, case 5, which is when t is equal to 3.5 or greater. Then we need to set up our limits for integration based on the overlap, and we end up with this integral.
Assalamu alaikum warahmatullah. This is Abdulaziz Musa, and this is the graphical method for solving the convolution integral y. There are five cases based on different ranges of t. In each case, the overlap between the function x and the time-shifted version h is visualized, represented, and the integral is evaluated by computing the area of this overlap. For case 1, where t is less than 1, there is a zero convolution result because there is no overlap between x and h. While for case 2, a partial overlap occurs as h starts shifting into x. For case 3, the overlap increases further. The integral now incorporate two segments of the shifted function. For case 4, at this stage, there is a maximum overlap. With contribution from both overlapping rectangulars, the integral becomes more extensive as the overlap reaches its largest size. Lastly, the overlap decreases as h shifted out of x and leading to smaller result.
Good evening, my name is Gabriel Gani Shane, and I will be sharing on the solution using MATLAB, where we perform convolution. So to perform convolution on MATLAB, we first define our signals, xt and ht. xt, which is negative ut minus 1, and ht will be 2 ut minus ut minus 1, subtracted with 1.5 ut minus 2 minus ut minus 2.5. Which is where the signals are actually given in the introduction as presented by my teammate. Now first here, we will plot both the signals xt and ht and set the x limits at negative 5 and 5, and the y limits at negative 2 and 1 here. Moving on, we will set the amplitude of the convoluted signal here, time t, convolution xt results, and so on. And this function conv result is where we convolute the whole, both the two signals, and scale it by 0.01. And after we run this, we will get the xt signal here, the signal ht right here, this, and then on the right we have our convoluted signal. And I'll pass it on to Gergis.
And as we saw by my friends, the relationship between xt and ht illustrate gradual modification of one signal by another. And yt, which is calculated manually by examining overlapping intervals while performing convolution, matched exactly the MATLAB simulation, following adjustments for particular ranges as shown in the simulated output. And that's it for our group.